Hi, welcome back to My Smart Learning. This is Mr. Meehan with your science and physics lesson. This is a lesson for year 9s, for your science GCSE, for physics and science, but it's also useful for year 10s and 11s because it goes all towards your GCSE exams. We're looking at gas pressure today, and this is the last of chapter 6. So chapter 6 is all about particles in your physics caboodle textbook. So just to finish off, over the last few weeks I've been going through the energy topics and we've sort of tied in the particles topic with it. So just to finish off, your recall quiz will be on some of the equations. Learning objective: what causes and affects gas pressure? That's our learning objective for today. But recall quiz, high five, you won't get your virtual high five because you can't buy those in the shops now that they're going to be opening in a couple of weeks time. You still won't find them in the shops. However, number 1, GPE equals, number 2, KE equals, number 3, E equals, now this is the one to do with power. Think about how power and energy are related. Number 4, E equals, talking about specific heat capacity, what's that one? And number 5, from our previous lesson, when we looked at latent heat, E equals what? Okay, press pause, have a go at answering those questions, and if you're done, we'll go through the answers now if you've pressed on pause. Right, GPE equals mgh, correct? GPE equals mgh. KE equals what? Half mv squared, half times mass times velocity squared. E equals, remember we did power. Power is energy divided by time. It's that PET equation, P equals ET. So therefore E equals P times T. So energy is power times time. And from looking at the particles and the energy within particle stuff, E equals mc theta. E equals m for mass, c for specific heat capacity, times theta, which is the change in temperature. So change in energy, delta E equals m delta c delta theta. Well, not delta c, sorry, mc delta theta. And the last one, E equals mass times latent heat. E equals ml. E equals mass times latent heat. So what we're looking at today, we're looking at pressure caused by gas. But as a starter activity, I want you to explain these phenomena after you witness Meehan's mysterious, mystical, marvelous, mega magic extravaganza. Woohoo! Right, what is it? Now, if you were in the science lab, if you were back at school, you'd have got to see, as a demonstration, a big, magic, massive science, amazing extravaganza. I like to call Meehan's mysterious, mystical, marvelous, mega, magic extravaganza. However, it's not going to be that extravagant here because I'm going to do it at home, because I'm not in the lab, because I don't live in a science school, in the science department, in the lab, in a box, in a cupboard somewhere. I do live in my house, and I could only get some of this stuff. So I can get the first one. Can you explain the cup and paper one? The aerofoil I can show you. The Magdeburg hemispheres I'm not going to be able to show you because they're at school. And the collapsing can I won't be able to either. But I'll talk you through those two. Right, cup and paper. Right, you may have seen this before. I've got, a bit over here before I do my back in. Right, I've got a bowl of water. Okay, just normal plain old water. It's nothing mysterious or magical about it. It's not acid or anything, because look, I dipped my finger on it. I'm not going to need my safety goggles. I'm not in science lab, and plus nothing's going to explode. If I was in the science lab, one of these would have imploded. There's my bowl of water. And I've got my favourite cup, my Peppa Pig cup. There are other cups available. So I've got my cup. I've got my bowl of water. All I'm going to do is fill up, if you can see it, I can put my cup into the water so it's completely full, and I'm going to do that. So hopefully this will work. I haven't tried it at home, tried it in school many a time. So I've got my cup and I've just got a piece of card. Now I know it says blue tack, nothing sticky about it. Look, it doesn't stick. It's got no blue tack in it. It's completely empty. Look, nothing in there. It's just a piece of card. It's the only piece of card I can find. And what I'm going to do is I'm going to put the piece of card on there, and I'm going to tip it upside down. And what's going to happen? What do you think is going to happen when I tip it upside down? Now I'm hoping you're thinking it's going to just tip upside down and all the water will come out and people in my household will kill me dead. We'll tip it upside down, and can you see? Hopefully I got it in the camera shot. If I let go. Ooh. Mian's mystical magic extravaganzas worked. Sometimes it flops, sometimes it doesn't, but that time it worked. Right, so can you explain why that's happened? How come that water is in there? Okay, I've just got a piece of card, nothing magical about it. It's not got any blue tack or any glue or anything in there. And I can even put my head under it. Did you see that? Right, so there. I was that, confident in the laws of physics that wasn't going to land on my head, right? And made a right fool of myself in front of millions of people around the world. Not that millions of people are watching it. There's only a few of you. But anyway, there, look, the water's still in there. If you don't believe me, oops. I just landed on my carpet. So you can hear, yep, there's water still in there. Now it's empty. Right, and it's not because it's got glue or anything, because look, it's not sticking anymore. So why did that happen? So, reason, think about the lesson what it's about, gas pressure, air pressure. Air pressure caused that. The pressure of air around you, okay, is caused because there's air in the atmosphere all around you pushing on you right now. But why don't you feel it? You don't feel it because inside of you, there's blood pressure. There's pressure inside of you, pressure outside of you. The inside pressure is caused by your internal fluids, your blood flowing around, pushing outwards. The air pressure is caused from outside of you. The atmospheric pressure is pushing and squashing down on your head. But it doesn't squish you down because the pressure is equalized, it's balanced. Some of you may have had nosebleeds over the last few days because it's been getting quite warm. Why? The pressure might have gone down, the internal pressure might have increased, and it could have caused your blood vessels to dilate and burst because it couldn't handle the change in pressure. So air pressure is greater than the weight of that water pushing down, trying to push that card down and fall out, but the air pressure is counteracting it and keeping it intact, in place. So the water pushing down, the weight of the water, the air pressure pushing up, and equally they're in equilibrium, they're balanced, so it stays in place. So that's the explanation behind the cup and paper one. The aerofoil, the Bernoulli effect. I think I've just damaged my wing by dropping the water. I might have wrecked this one. All I've got is a piece of paper. I've just got a piece of glass slate just so that you can see it, so I can hold it in place. So just a piece of paper, and I've just folded it, put a line across there, and I've just folded it so it's just got an edge to it. So then if you look, I'm going to place the paper on the edge, and you can see the shape of it. I'm just holding that paper down. There's that shape where it's rounder and fatter at the front and narrower at the back. Now if you look at an aeroplane's wing, that's what it would look like from the side. And as the airplane flies towards me, like this way, that is the shape of the plane wing. Now, most people think the plane wings are just flat, like wings like that. They're not. When you look at the front, it's thicker. And you look at the back, it tails off, it becomes thinner. Okay, just like birds' wings as well. So, what is the Bernoulli effect? Well, think about what I've just mentioned. I've talked about aeroplanes, and I've talked about aerofoil. This is an aerofoil. And all I've done is I made the front bit fatter, the back bit narrower. And I'm going to blow onto this aerofoil. I'm going to blow across it. Now what do you expect to happen? If I blow onto something, what should happen to that paper? Now most people will say, well, if I blow onto it, the paper should blow down. Okay, so if I blow on, you can see it blows downwards. So if I blow across it, you'd think the same thing. Because look, if I blow down, it goes down. But what's going to happen if I blow across it rather than down? Now people think the same thing should happen because you're blowing onto the aerofoil. But watch, as I blow onto the aerofoil, the Bernoulli effect. Whoa, did you see that? It's coming towards me. Why is that happening? Is it because my house is haunted and I've got witches around? No. It's the laws of physics that I always trust. I always trust the laws of physics because it's got to work. For the biology experiment could have gone wrong, but right. It's lifting up, lift off. It's how airplanes fly. As the airplane with the wing shaped like that, the aerofoil, as it goes faster and faster and faster, as it cuts through the air, the wind is flowing over it, the air is flowing over a longer distance there compared to a shorter distance there. What tends to happen is you get the faster airflow over the top, the slower airflow over the bottom, but what happens is you get a buildup of air pressure here compared to here, so there's a higher air pressure beneath compared to the top. So if you've got low pressure and high pressure, it causes lift off, and that's what the Bernoulli effect is. But again, it's to do with air pressure and the change in air pressure. Two other experiments that I cannot show you at home because I don't have a Magdeburg hemispheres. They're just two metal cups, okay, like bells. Two bells facing each other, but they seal together there, and there's two handles on both sides, but on one side there's a little valve. And if I connect a vacuum pump to this valve here, and when I close it, I can suck all the air out from inside the middle of the Magdeburg hemispheres. And if I suck all the air out, what you've got inside is a vacuum. A vacuum, by definition, is somewhere where there's absolutely no particles at all. So in the middle of there, it's completely empty. There's no air particles, nothing. It's vacuum, just like in space. So outside of it is what's around you, it's atmospheric pressure, air pressure pushing down on it. Now, I can't show you these, but if you YouTube it, there are other videos on YouTube, and there's also, if I get a chance, we've got these at school, I'll show you. When you suck them out, you'd expect that if I just get the two handles and I pull it, I should be able to take them apart. But what you'll find is the atmospheric pressure is so strong. You see these red arrows? They're pulling really, really, really hard on it, and they're literally, two bodybuilders cannot pull them apart because the atmospheric pressure is so strong, it's so powerful that it holds these two things in place. When there's air inside and you open it, if you just release the valve, air goes back inside, they'll just come apart like this, pop, like that. But as soon as I take all the air out, there's a vacuum inside and there's air pressure on the outside, huge amounts of force cannot pull them apart. And they're called Magdeburg hemispheres, I think, because it's a place, I don't remember the story, I think it's Italy or something like that. If you look in the textbooks, you can see it. There's two horses that couldn't pull these Magdeburg hemispheres. They are these huge bell shapes, probably as high as me, the Magdeburg hemispheres were. And two horses were pulling in opposite direction. The horses, really powerful stallions, pulling these hemispheres apart. And they couldn't, because the force of air pressure showing you that they're extremely, extremely strong. The collapsing can experiment, the one I do at school, is I get a Coke can. There are other fizzy drinks available. But if you drink all the drink and you pour a tiny bit of water in there, about this much into the can, and I get a Bunsen burner and I heat the water up inside, the water starts to boil and evaporate out of the hole at the top of the Coke can. And then I get a special pair of tongs that holds the Coke can. I've got a big water trough like my bowl of water down there, and I just turn it upside down onto my trough of water. What happens is, as the hot water has turned to steam, it pushes all the air out of the can. As I quickly turn it upside down, it condenses really quickly. So when the steam condenses back, because the air has been pushed out, it leaves a partial vacuum inside. People think, oh, it's going to explode, but it's the complete opposite of explode, which is implode. It completely crushes and collapses inwards because the air pressure outside goes boom, like that, really loud bang sound. But what's happening is the can is not exploding. I've heard people screaming when they hear that bang. But what happens is the air pressure crushes it really quickly, instantly. If you blink, you miss it because it happens instantly. The whole can crushes into like a little crumb, like a little tiny crushed can. And that's the power of air pressure. Another way of showing you the atmospheric pressure using a vacuum on the collapsing can experiment is this. If this comes up, there's a collapsing can. Before, you got a can, you get a vacuum on it, you suck all the air out so it becomes a vacuum inside, and you'll see the can starts to crush. It's the crushing can, or the collapsing can experiment. Why does it happen? It's all to do with air pressure. So what you see here before, there's air inside. That pump will suck all the air out like that. Now what's going to happen is that the pressure outside is greater than the pressure inside. So therefore the forces will crush the can. Like you just saw there, if this works. There. Instantly you'll see the can crush like that. Okay? And there you go. Before the air is removed, and then after, as you take the air out, the air pressure starts to push on the, so at the beginning, while there's air still inside, the pushing of the air pressure, which is the gas pressure, is pushing against the can. The air pressure from the outside is also pushing against the can. They're equaled out, so they're in equilibrium. The forces are equal, so it stays in that shape. Once you remove the air pressure outside is greater than the pressure inside, so the force of the air pressure collapses and crushes that can. So, what causes pressure, gas pressure? The gas pressure is caused by the particles in a gas. Now, if you remember from a previous lesson, particles of a gas, they're all spread out and they're moving around really fast. They have lots and lots of kinetic energy. And the higher the temperature, the higher the kinetic energy they'll have. They move around even faster, the greater the pressure will be if I increase the temperature. Okay, because I'm giving them more kinetic energy, giving them more energy, so they move around faster, more velocity, v squared, remember k equals half mv squared, and they smash against the sides. So if I heat up a can, the pressure, if it's enclosed, the pressure is going to build up and build up and build up. Eventually it can explode, it'll pop. And that's why pressurized cans, we should never heat up pressurized cans like a can of Lynx or something. If you put it in a fire, they'll explode because they won't contain that pressure inside. So pressure is caused by the repeated striking against the walls of the container because the particles are bouncing around on the inside. But for a fixed volume of gas, the fixed number of particles and a fixed temperature, the gas pressure would remain same. But if I wanted to decrease the volume, if I made the volume less, what would happen to the pressure? Well, if I made the walls come in closer, that ball will bounce around quicker because it's got less distance to go. What's going to happen to the pressure? Well, the pressure is going to increase. And this is what we're going to move on to now. The idea, first of all, is that the gas pressure is caused by the movement of gas particles inside a given container. The faster they move, the greater the pressure, because they have more kinetic energy, they'll hit the sides with more force, with more energy, therefore there'll be greater pressure. So, how can I make the pressure increase? I can either increase the temperature or I can reduce the volume, because the volume makes it less space to move around, so they will whack around the insides more frequently. However, if I make the space bigger, make the volume larger, the particles got further to go, pressure will decrease. And if I lower the temperature, make it cooler, the particles will move slower, and therefore they'll have less pressure too. So, also, if you've got a fixed number of particles, if I've got a tyre and it's deflated, I want to inflate the tyres, I obviously put more particles in there. All I'm doing by inflating my tyre is putting more air into my tyre, and that's going to increase the pressure. Why? Because I've increased the number of particles, therefore they're going to move around and hit those sides. There's more frequency of collisions, more probability that they're going to hit the sides. So it's to do with the number of particles too. But in this system, what we're talking about today is when you've got a fixed number of particles. So you close the lid, you close the cap, there's no gas going in, there's no gas coming out. It just stays whatever's inside there. So when I increase the temperature, or I make the space smaller, the pressure will rise, and vice versa. If I make the space bigger and I reduce the temperature, the pressure will fall. Now, how do they come up? How do they know what gas particles move around like? This is called Brownian motion, named after a scientist. And what he did was he looked at some smoke under a microscope. And so you got the light shining on the smoke. He's got the microscope, and he can see the smoke particle there. You can't see gas particles. They're too small. They're individual particles or molecules moving around really fast. So how do we know what they move around like? Well, what you can see though is smoke, because smoke is large particulates, really big. And what he noticed when he looked under the microscope in this Brownian motion is that you can't see the gas particles, those blue ones, but that big soot there, the gas of smoke, you can see the particles of the big lumps of smoke particles, okay, charcoal bits there. And what it looks like under a microscope is jiggling around, randomly jiggling around, like random like that. So, but you can't see what's causing that. So that's where we came up with the idea that gas particles must be colliding and smacking into that smoke particle, and therefore it's random because they're not moving. It's not moving in a perfect rhythmic symmetrical way. it's like jiggling around in all sorts of random ways. So we call it Brownian motion, named after this observation that they made under the microscope with smoke. So that gas particles are moving around randomly and rapidly and very, very fast, and they bounce off things. And that's how we come up with the idea of gas movement, the particles, how they move. To finish off then, up till now, what we've just looked at so far is for the trilogy as well as the separate sciences. Now the Boyles Law section I'm looking at now is actually only in the GCSE physics paper. So people that are doing trilogy, they don't need to know about this bit because it goes on to a bit of a higher level. It's useful to know anyway. If you want to become a scuba diver, you know, like diving under the ocean, if you want to have that certificate, it's called a PADI, P-A-D-I, PADI certificate. I've got one in Thailand when I was traveling. You have to do an exam. You go to your practical exam, you have to swim like 30, 40, 50 meters in the ocean. You have to do another one where you're floating in the ocean for so long. Then you have to do another one, you're diving under the ocean. Then you have to go under the ocean when you've passed there's a written exam that you have to pass just to be allowed to scuba dive freely under the ocean. You learn all about the equipment, the buoyancy aid, the buoyancy device, your gas tank that you have to wear, your air tank as you go under the ocean when you go scuba diving. But you've got to do a bit of physics. You've got to do a bit of chemistry and physics to understand what happens to gas pressures as you go underwater. I didn't think I'd ever come across it again traveling around the world, but I did when I had to do this test. So you have to pass an exam to get your PADI certificate, so you're allowed to go open water diving. And the question came up was about Boyles Law. What is Boyles Law? Boyles Law is this: the pressure times the volume. Okay, if you've got a given fixed number of particles, P times V is what we call the gas constant for any given gas. There's a fixed number. What does it mean? Basically, for a fixed mass of gas, a fixed number of particles of gas at a fixed temperature, the volume is inversely proportional to the pressure. What does that mean? It's a very mathematical term. Remember, if something's directly proportional, it means that if you've got y and x axes, if it's directly proportional, you get a straight line going up like this. That means if I double something, I double that. If I double the x, I double the y. If I triple the x, I triple the y. It goes up proportionally to each other. Okay? But if it's inversely proportional, it's the opposite way around. It means it's going down the opposite way. But it's like y is proportional to 1 over x. Basically meaning it's the opposite way around. You inverse it, 1 over that number. Now what does that mean? So for a given pressure, the volume is inversely proportional. So this little funny alpha symbol there is just a proportional sign. P is proportional to 1 over V. What does that mean? I could rearrange that to get the gas constant. So to get rid of the proportionality sign, this is going to high level GCSE paper maths now and for physics. To get rid of that proportional sign, to put an equal sign in there, I need what we call a constant of proportionality. To put constant in there, to get rid of that proportional sign, to put an equal sign in there, I can rearrange that. I can times it by the velocity. If I put k there to get the constant of proportionality, so that 1 becomes a k, that becomes P equals k over V. And to get the V over to that side, I times it by V to that side, that makes it disappear on this side. So PV equals K. So there you go, PV equals K. The pressure, which is measured in pascals, the volume, which is in meters cubed, gives you the gas constant, we call it. Now, what does it all mean? Easiest way to understand this is this. Look at this graph here. If I increase the volume, the pressure decreases. So as I increase the volume, the pressure decreases. But it doesn't decrease in a uniform way. It doesn't a straight line. It's inversely proportional. So what happens is it starts to curve like this. And I've already explained the reason why. If you increase the volume, there's more space for the particles to move around, the gas particles to move around. So therefore they got further to go, they got longer to go to hit the sides. The pressure starts to decrease, but not in a uniform way. It decreases in this kind of curved manner. And we call that inversely proportional. So it's inversely proportional. So as I increase the V, the pressure decreases. So if I decrease the volume, so make the volume less, you can see it doesn't go up in a uniform way like in a straight line. It actually starts to curve exponentially. So as I increase the volume, so as I decrease the volume this way, so as I decrease the volume, so I've got smaller space, the pressure increases, but not in a direct way, in a proportion, in a exponential way there, you can see. So that's the end of that then. So what we've been learning about is key points. The pressure of a gas is caused by the random impacts of gas molecules on surfaces that are in contact with the gas. If the temperature of the gas is in a sealed container is increased, the pressure of the gas increases because the molecules move faster, so they have hit the surfaces with more force. The number of impacts per second of the gas molecules on the surface of a sealed container increases, so the total force of the impact increases. The unpredictable motion of the smoke particles is evidence of the random motion of the gas molecules that we just said. And the last thing, for a fixed mass of gas at constant temperature, its pressure is increased if its volume is decreased and vice versa. And reducing the volume of a gas increases the number of molecular impacts per second on the surface that are in contact with the gas. And the equation is PV equals the gas constant if the mass and the temperature of the gas do not change. Remember, they have to have the same number of particles, so the mass can't change and the temperature can't change, because by giving the increase in temperature, you're giving more internal energy, therefore they're going to be moving around faster, they hit faster. And the higher paper, the temperature of a gas can increase if the compress rapidly because the work is done on it and its energy isn't transferred quickly enough to its surroundings. What does that mean? If you imagine I've got a gas inside a canister and I quickly suddenly increase the pressure, the temperature actually obviously rises because work is done. I have to put work in to squash that gas into a smaller space. So if I do it slowly and I increase the work done into it to squash it down, if I do it slowly, that energy that I'm transferring in can dissipate into its surroundings. Therefore, the temperature of that gas won't increase. If I go really fast, because I haven't given time for the energy to dissipate into the surroundings, go really, really quick into the, you can kaboom, but the temperature of the gas rises. This is higher paper physics understanding, and it's going on to sort of A-level content as well. So that's the end of that. There's some exam questions for you to have a go at. It's going to be all posted on Show My Homework for you Year 9s to have a go at. If you learned something today on My Smart Learning, that's fantastic. And I forgot to give you a virtual high five. Hopefully you've learned something today, and I hope to see you next time. Your virtual high five is coming now. Take care.